Welcome to ASAP Marima!
So since our topic is about absolute zero, first thing we have to identify what is absolute zero. So absolute zero is a cooled ideal gas at a minimum value. Meaning, for example, let's say we have two identical boxes, but the only difference that we can see is in the particles, meaning that here the particles are more active, meaning that the temperature is high. So let's say high or hot. Here the particles are less active. Why? Because the temperature became lower. So here it's low, and then it becomes lower and lower. What we can conclude about absolute zero is as the particles become lower, it's approaching 0K, which is absolute zero.
Okay, so one of the first people to discuss the possibility of absolute zero was a scientist by the name of Robert Boyle. In the late 1665s, he started discussing and making experiments about absolute zero, which brought up a dispute and arguments between scientists called as the premium frigid discussion. They started articulating and discussing the possibility of obtaining such a thing. The one thing that they seemed to agree on was that there is a natural substance in the known universe that on its own is supremely cold. And by contact of the supremely cold object, the other material would obtain this coldness and obtain like the other values of this substance. Okay, so what happens at absolute zero? Theoretically, everything's supposed to stop at absolute zero. Everything's supposed to come to rest and measure to zero. But in reality, due to quantum mechanics, they can't actually measure the exact position or momentum of particles with perfect certainty. So they can't ever actually be certain that the particles, when they got to absolute zero, measured to zero. This is due to the Heisenberg uncertainty principle. Now let's assume you have a room. In this room, you have managed to seal it down, and the temperature in it right now is 0 Kelvin. Okay. For one, the pressure, what's gonna happen in this room, the pressure for one is gonna get to 0. And another thing, the particles in the room are gonna become superconductive and superfluid. And since the pressure got to 0, it's the air pressure that normally resists gravity. So what's gonna happen to the air? It would collapse to very thin layers on the floor. Okay, but let's actually hypothetically say that you were able to measure the speed of the particles in that are actually in this room. You'd actually be surprised, and they wouldn't actually say 0. The particles in this room would still be vibrating and moving. This is a perfect example of the Heisenberg uncertainty principle.
The next topic that we'll be talking about is the coldest natural place in the universe. Generally speaking, the average temperature of the universe is approximately 2.73 Kelvin, based on measurements of cosmic microwave background radiation, which is known as the Big Bang.
Okay, so negative Kelvin. Getting down to absolute zero has essentially the same problem as trying to get up to the speed of light. Getting to the speed of light would require an infinite amount of energy, while getting down to absolute zero would require extracting an infinite amount of energy. Now let me just say this. Our outer space is only 2.73 kelvins, which was caused by the microwave radiation left over by the Big Bang. Now the coldest natural place in our known universe is the Boomerang Nebula, measuring at 1 Kelvin. To do this, physicists have created an atomic gas with a sub-absolute zero temperature for the very first time. Their technique opens up to generate negative Kelvin, which can be later on used to create new quantum devices, and it can even help solve cosmological mysteries. Physicists later realized that the absolute temperature of a gas is related to the average energy of its particles. Absolute zero corresponds to the theoretical state in which particles have no energy at all, and higher temperatures corresponding to higher average energies. Okay, so for us to comprehend negative values and negative temperatures scales, scientists have started to devise a different type of scale. So rather than it being like the type of scale that we know of, which is the linear scale, they devised a different one. They they thought of it as a loop. Okay, so let's say here you're gonna have +0, and you're gonna start to heat up the particles, and they're gonna start to move on to +infinity. The particles are just gonna keep rising, and at one point they're gonna get to the negative realm, which is -0. But you need to keep in mind that even though they hit -0, the particles are not cold. They're not getting colder. They're actually getting hotter than any other temperature at a positive scale. So as they're moving on from +0 to +infinity, they're not, and to -0, they're not getting colder. They're actually getting way hotter, and then they start moving on to -infinity. At this point, they got way more hotter than any other temperature that a positive scale could have thought of. And then the loop just keeps moving on. And the more they move on, the hotter the thing gets. Even though they're at a negative scale, the particles keep moving faster and getting hotter. This whole concept of -infinity was discovered by a scientist in Germany. His name is Ulrich Schneiden. His principle is basically that the temperature scale simply does not end at infinity, but it jumps to negative values instead. As one might expect, objects with negative infinities behave in very odd ways. For example, we all know that energy typically flows from objects with a higher positive temperature to ones with lower positive temperature. However, in the negative realm, energies will always flow from objects with negative temperature to ones with positive temperature. In this sense, objects with negative temperatures are always way more hotter than objects with positive temperatures. This is why the energy will move on from a negative infinity to positive infinity.
Next up, we want to know how to obtain negative Kelvin. So scientists, they created the system where atoms do have a limit to much energy that they can possess. First of all, what they did is that they cooled around 100,000 atoms in something called a vacuum chamber. This vacuum chamber, they isolated it from any environmental influence that could potentially heat the atoms or the particles again. So what is it called? The temperature that these scientists achieved, it was -nanokelvin, and nano is 9 in physics. Temperature, in general, temperature depends on how much energy the atoms have, but when they isolated these atoms away from the environment, it started to cool down, and it reached to them obtaining the -Kelvin. Okay, so now we're going to be discussing Gay-Lussac's law and how is it related to absolute zero. First of all, as we all know, when gas is heated, its molecules' average speed and kinetic energy, they increase as well. Let's say we have a container and it has a constant volume. The gas particles are going to be all over the place. They will strike its sides with greater frequency. This creates greater force on the container's wall, and that will increase pressure in the container. Now, how is this related to absolute zero? First of all, we need to have an extrapolation to zero pressure, because it's necessary to for gas, because real gases, first of all, they condense into liquids and then they solidify before becoming absolute zero. Now, the relationship between the pressure of an ideal gas and its Kelvin temperature is expressed in this, the Gay-Lussac's law, which is P1 over T1 equals P2 over T2. Wait, yo. Oh, wait. Yo. Today, we're talking about. Wait, start talking. We're talking about A, Z. With lemonade together forever. Na-na-na-na. You're gonna learn, you're gonna understand.
This upstairs should be like, hey guys, so we're back, and this time we're just